Have you seen colors in CD and the natural phenomena that we are observing around us? Shadow cast by an opaque object close to the regions of the geometric shadow. These are all due to a very important phenomenon of light called diffraction. Now we are going to study a very important phenomenon of light called diffraction. What is diffraction? The bending of light around the obstacle or aperture and the consequent spreading of light into the regions of geometric shadow is called diffraction of light. Okay, so diffraction of light means the bending of light around the obstacle or aperture. Diffraction is considered to be a wave phenomenon and it is exhibited by all types of waves like water waves, sound waves, light waves, matter waves, etc. Here, a person standing outside the room can hear the sound, but the person standing outside cannot see the person inside the room. Okay, the person standing outside can hear the voice but cannot see the person. That is, both sound waves and light waves undergoes diffraction. That means sound waves bend around the obstacle, similarly light waves also bend around the obstacle. Okay, but why diffraction of light is not seen in day-to-day activities? The reason is diffraction effect is observed only if the size of the aperture or obstacle is comparable with the wavelength of the waves. So, this is a necessary condition for diffraction to be observed. The size of the obstacle or size of the aperture should be comparable with the wavelength of waves. In the case of light, the wavelength is much smaller, of the order of 10 raised to minus 7 meter. Okay, wavelength of light, visible light is of the order of 10 raised to minus 7 meter and it is very small. But what about the size of the obstacle or aperture around us? The size of the obstacle or aperture around us is much larger, it is of the order of meter. But wavelength is of the order of 10 raised to minus 7 meter. It is very small and they are not compared. Okay, they are not comparable and hence diffraction of light is not seen in our day-to-day activities. This is the reason. Okay, so diffraction is taking place but it is not observed in day-to-day activities or it is not pronounced in our day-to-day activities. The reason is this condition is not satisfied. So, what is the condition for diffraction to be observed? The condition is the size of the aperture or the obstacle should be comparable with the wavelength. In the case of light, wavelength is small and the size of the aperture is much greater and they are not comparable. But what about sound waves? Sound waves have larger wavelength and it is comparable with the size of the obstacle around us. The wavelength of sound waves are of the order of meter and the aperture or obstacle around us is also of the order of meter and both can be compared and hence sound wave diffraction taking place in our day-to-day activities but diffraction of light is not seen in our day-to-day activities. Okay children, and hence sound waves get diffracted by objects around us. Now colors in CD, the finite resolution of our eye, optical instruments, finite resolution of optical instruments like telescope, microscope, etc. is limited due to the phenomenon called diffraction. Now we can discuss the single slit experiment for diffraction pattern. In the previous class we have studied double slit experiment for interference pattern. Here we can discuss single slit experiment for diffraction pattern. Okay, so consider a single slit. This LM represents a small slit. Actually this is of the order of millimeter. Okay, this is a small slit, small opening, and consider a monochromatic source S and it is placed very close to the slit. And consider a screen which is placed at a distance capital D from the single slit and the width of the slit is small a. Clear children? So, consider a small slit of width A, it is placed in front of the original source. Consider a screen which is placed at a distance capital D from the single slit. Here O be the sender and consider a point P which is at a distance, we can write at a distance y. Example, at a distance y from the center region. Consider a monochromatic source S is placed behind a single slit SLM of width A. This is single slit LM of width A and the monochromatic source is placed behind it. Consider a screen is placed D from the single slit. Here this is a screen which is placed capital D from the single slit. And what is the cause of diffraction? We know interference is due to the superposition of two wavefronts. Okay, two wavefronts from coherent sources. Similarly, diffraction is due to the superposition of wavelets starting from different points of the wavefront. So here this is the source, around it there is a wavefront. Okay, so on the wavefront there are number of points and number of wavelets can also be drawn, and the superposition of the wavelets corresponds to diffraction pattern. So diffraction pattern is due to the superposition of wavelets from different portion of the wavefront. Okay, that is the cause of diffraction. So at the point O, wavelets superimpose. At the point O, wavelets from this region of the slit reaches the point O, wavelets from the bottom region of the slit reaches the point O, and they superimpose to form central maximum or central bright fringe at the point O. So at the point O, LO and MO are equal. So what is the path difference? Path difference is equal to 0, phase difference is equal to 0, and hence at the point O a central maximum or bright fringe is formed. In interference pattern also at the center maximum bright fringe is formed. Similarly, in diffraction pattern also at the center region a bright fringe or maximum, central maximum is formed. Now we can calculate the path difference. So draw a perpendicular from L to MP. Okay, let it meet at the point Q. And theta is the angle of diffraction. So draw a perpendicular from L to MP, and theta is called angle of diffraction. The path difference between wavelets from L and M is, what is the path difference? Path difference between wavelets from L in reaching the point P and M in reaching the point P is MP minus LP. So path difference is MP minus LP. And here this MP can be written as MQ plus QP, isn't it? MP can be written as MQ plus QP minus this LP. Okay, since this width A is very small, theta is also very small, QP and LP are approximately equal. Okay, so the angle of diffraction theta is actually very small. Slit width is also very small. So QP and LP are equal, therefore path difference can be written as MQ. So this is the path difference. Okay children. Now from the triangle LMQ, consider triangle LMQ. Take sin theta. What is sin theta? Sin theta equal to opposite side, which is MQ, divided by hypotenuse. This is 90 degree, no? So what is the hypotenuse? LM represents the hypotenuse. Okay, so MQ divided by, what is the value of LM? LM is equal to the slit width A. So MQ can be written as A sin theta. So therefore path difference between the wavelets from L and M is, path difference is equal to MQ equal to A sin theta. So we got the value of path difference as MQ equal to A sin theta. Here we can make an approximation. Since the value theta is very small, sin theta is approximately equal to theta. Using the sine series we can write theta is very small, sin theta is approximately equal to theta. Therefore path difference is given by, what is the value of path difference? A sin theta, but sin theta is very small, no? So sin theta is approximately equal to theta. Therefore path difference is given by A theta. Clear children? So the calculation of path difference in diffraction pattern is, path difference is equal to A theta. Now we can derive the conditions for maxima and minima. Here in diffraction pattern the bright fringes are called maxima and dark fringes are called minima. First we can obtain the condition for minima. Let path difference is equal to 1 lambda. Path difference between the two wavelets, let it be 1 lambda. Now we can divide the slit LM into two parts. If path difference is equal to 1 lambda, we can divide the slit into two halves, this part, and each wavelet having the path difference lambda by 2. Okay, so let the path difference is 1 lambda, the slit is assumed to be divided into two halves, and each wavelet from each half Wavelet from each half having a path difference lambda by 2. Okay, since it is 1 lambda. So what will be the phase difference? Path difference lambda by 2 means phase difference is 2 pi by lambda into path difference, no? So relation between phase difference and path difference is, phase difference is 2 pi by lambda into, here the path difference lambda by 2. So phase difference is pi. So first wavelet from the first wavelet can be written as y1 equal to a cos omega t. Second wavelet can be written as a cos omega t plus the phase difference pi. What is cos omega t plus pi? We know it is minus cos omega t. Okay, so y2 equal to a cos omega t plus phi. Cos omega t plus phi is minus cos omega t. Therefore, y2 can be written as minus a cos omega t. So, this is the first wavelet and this is the second wavelet. And how will you write the resultant wave? A resultant wave can be written as y equal to y1 plus y2, it is equal to 0. Okay, so if path difference is 1 lambda, assume that the slit is divided. The slit LM can be divided into 2 halves and each wavelet having path difference lambda by 2, and so that the phase difference become pi. First wavelet can be written as a cos omega t, second wavelet can be written as y2 equal a cos omega t plus pi, because phase difference is pi, isn't it? So, it is minus a cos omega t and the resultant is equal to 0. Resultant is 0 means intensity is 0. So, that is the condition for first minima. So, the condition for first minima is path difference is equal to 1 lambda. So, this is the first case. Now, if path difference is equal to 2 lambda, we can assume the slit is divided into 4 parts. 2 lambda, no? Lambda by 2, lambda by 2, lambda by 2, lambda by 2. The slit is assumed to be divided into 4 parts and the wavelet having path difference lambda by 2. Here also phase difference is pi, because 2 pi by lambda into lambda by 2, which is pi. Here also they superimpose to form 0 intensity, same as the first case. So, this is the condition for second minima. So, for second minima also resultant intensity is 0 and the corresponding path difference is 2 lambda. Similarly, if path difference is equal to 3 lambda, we can divide, the slit is assumed to be divided into 6 parts, 3 lambda, no? Lambda by 2, 6 times. Here also path difference between the two wavelet is lambda by 2. Phase difference is pi. Here also resultant intensity is 0. That means here which minima is formed? The third minima is formed. So, if path difference is equal to 1 lambda, that is the first minima. If path difference is equal to 2 lambda, that is second minima. If path difference is equal to 3 lambda and third minima. Hence, we can generally write the condition for minima. Condition for minima is, the condition for minima in diffraction pattern is path difference. What is the value of path difference? A theta, no? Path difference is equal to n lambda, 1 lambda, 2 lambda, 3 lambda, etc. Or path difference is equal to n lambda. Okay, path difference is equal to n lambda. What are the values of n? N equal to 1, 2, 3, 4, etc. If n equal to 1, path difference is 1 lambda, that is first minima. If n equal to 2, path difference is equal to 2 lambda, that is second minima. If n equal to 3, path difference is 3 lambda, that is third minima, and so on. So, the general condition for minima is path difference is equal to n lambda. Clear, children? So, the condition for minima in diffraction pattern is path difference A theta is equal to n lambda. So, here A theta, if n equal to 1, A theta equal to 1 lambda, that is the condition for first minima. If n equal to 2, A theta equal to 2 lambda, that is the condition for second minima. If n equal to 3, A theta equal to 3 lambda, that is the condition for third minima, and so on. Now, we can derive the condition for secondary maxima. In diffraction pattern, the maxima, bright fringes are called secondary maxima. Okay, central region is called central maxima and other bright fringes are called secondary maxima. First we can take, let path difference is equal to 1.5 lambda. Okay, if path difference is 1 lambda, 2 lambda, 3 lambda, 4 lambda, etc., minima are formed. Similarly, if path difference is equal to 1.5 lambda, the slit is assumed to divide it into how many parts? 3 parts. Okay, because each one having path difference lambda by 2. So, lambda by 2 into 3, that is 1.5 lambda. Okay, so if path difference is 1.5 lambda, the slit is assumed to be divided into 3 parts. And the path difference between the first 2 parts of the slits will be lambda by 2. So, they superimpose to form 0 intensity. And these wavelets interfere destructively. That means the first 2 wavelets superimpose which forms 0 intensity. Okay. But however, the third part of the slit contribute to some intensity. But there is no another wavelet for the third part to superimpose. So, the third part only contribute to some intensity and hence intensity is only due to 1/3 part of the slit. First 2 parts superimposed to form 0 intensity. So, intensity is only due to 1/3 part of the slit and hence that is called first secondary maxima. If path difference is 1.5 lambda, that is the condition for first secondary maxima. Now, if path difference is equal to 2.5 lambda, in how many parts the slit has to be divided? 2.5 lambda means the slit has to be divided into 5 parts. The first 4 parts superimposed to form 0 intensity and the intensity is provided by only which part of the slit? 1/5 part of the slit. So, intensity is provided by 1/5 part of the slit and hence the 5th part of the slit contribute to some intensity forming the second secondary maxima. Okay, so if path difference is equal to 2.5 lambda, the slit is assumed to be divided into 5 parts and the intensity is provided by 1/5 part of the slit. So, that is the condition for second secondary maxima. Similarly, if path difference is equal to 3.5 lambda, that will be the condition for third secondary maxima. Clear children? So, the condition for secondary maxima is path difference a theta equals 2n plus 1 into lambda divided by 2. So, this is the condition for secondary maximum in diffraction pattern. So, path difference is a theta is equal to 2n plus 1 into lambda by 2. What are the values of n? 1, 2, 3, etc. If n equal to 1, that is 3 lambda by 2, that is the first case. 1.5 lambda, that is called the first secondary maxima. Put n equal to 2, that is 5 lambda divided by 2, that is 2.5 lambda, that is the condition for second secondary maxima and so on. So, here the values of n are 1, 2, 3, 4, etc. Clear children? So, the condition for secondary maxima in diffraction pattern is path difference is 2n plus 1 into lambda by 2 and the values of n are 1, 2, 3, 4, etc. So, a theta is equal to 1.5 lambda, put n equal to 1, 1.5 lambda, that is the condition for first secondary maxima. A theta is equal to 2.5 lambda, that is the condition for second secondary maxima. If a theta is equal to 3.5 lambda, that is the condition for third secondary maxima. Clear? So, this is the general condition for secondary maxima. A theta is equal to 2n plus 1 into lambda by 2 and the condition for minima is a theta is equal to n lambda. Now, we can draw a graph relating intensity and path difference in single slit diffraction pattern. Variation of intensity with path difference in single slit diffraction. We know the condition for minima in diffraction pattern, the condition for minima is path difference is equal to n lambda. This is the condition for minima and the condition for maxima is path difference is 2n plus 1 into lambda by 2, that you know. So, at Here graph is plotted with intensity along the x-axis and path difference is a theta. It can be plotted along the y-axis. We know that at 0 path difference is equal to 0, that is central maxima. If path difference is 1.5 lambda, that means first secondary maxima. If path difference is 2.5 lambda means second secondary maxima. Path difference 3.5 lambda means third secondary maxima, and so on. But what about the intensity? Intensity goes on decreasing, because here in the first case, for the first secondary maxima, intensity is provided by 1/3 part of the slit. In second secondary maxima, intensity is provided by 5th part of the slit, 1/5 part of the slit, and so on, isn't it? So intensity goes on decreasing in diffraction pattern. So we can draw the graph like this. So here this is the graph. Here this represents a central maximum where the intensity is maximum. This is the central maximum, central bright fringe. Intensity is maximum. At 1.5 lambda, intensity decreases because it is provided, intensity is provided by 1/3 part of the slit. Now at 2.5 lambda, if path difference is 2.5 lambda, intensity again decreases because intensity is provided by 1/5 part of the slit. At 3.5 lambda, intensity again decreases because here intensity is provided by 1/7 part of the slit. Here 1/3, 1/5, 1/7. Clear, children? So here intensity goes on decreasing. Here this is called central maxima. This is called first secondary maxima. This is called second secondary maxima, and this is called third secondary maxima. On the other side, this represents first secondary maxima on the other side. Here also second secondary maxima, this one third secondary maxima. Clear, children? Now, here this corresponds to between 0 and 1.5 lambda, there is a dark fringe or minima, and this corresponds to 1 lambda. This corresponds to 2 lambda. We know that at 1 lambda, 2 lambda, 3 lambda and all minima are formed. So at 1 lambda first minima, 2 lambda second minima, 3 lambda third minima, and so on. On the other side also same. So this corresponds to minima. So this is the graphical representation of intensity with path difference. Here this shows that intensity is maximum, then for the secondary maxima intensity goes on decreasing. Now we can discuss all the formula relating diffraction. We know the condition for secondary maxima is path difference a theta equal to 2n plus 1 into lambda by 2, and here n equal to 1, 2, 3, 4, etc. Condition for minima is path difference is equal to a theta equal to n lambda. Here also n is equal to 1, 2, 3, 4, etc. Okay. Now, what is the angular fringe width of central maxima? Angular fringe width of central maxima, here we know this is the maxima, no, central maxima. So here a theta is equal to 1 lambda, here also 1 lambda. So what is this value? This is equal to 2 lambda. A theta is equal to 2 lambda. Okay, children. So central maxima, for the central maxima the whole region is a theta is equal to 2 lambda. So what is theta? 2 lambda by a. And that is called angular fringe width of the central maxima is theta is equal to 2 lambda by a. Now what is the angular fringe width of all secondary maxima and minima? If you consider this one, secondary maxima, here this is 2 lambda, here also 2 lambda. What is this distance? That is corresponds to a theta is equal to 1 lambda, here this region 1 lambda, here also 1 lambda, here in this region also 1 lambda. Okay, so for angular fringe width of all secondary maxima is a theta is equal to 1 lambda or theta is equal to lambda by a. So angular fringe width of central maxima is 2 lambda by a, and angular fringe width of secondary maxima and minima is lambda divided by a. Now linear fringe width of central maxima. Linear fringe width. We know angular fringe width. What is the relation between angular fringe width and linear fringe width? Angular fringe width is equal to beta divided by d. Okay, angular fringe width is equal to linear fringe width divided by d, or beta equal to d theta. So, if theta is known, theta means angular fringe width is known. If it is multiplied by d, we will get the linear fringe width. So, linear fringe width of the central maxima is 2d lambda by a, and the linear fringe width of all secondary maxima is d lambda by a. Okay. So, in the diffraction pattern, the central maxima have double width. Central maxima has double width than secondary maxima and minima. So, that is the main difference between interference pattern and diffraction pattern. In interference pattern, all the bright fringes and dark fringes are same width. But in diffraction pattern, central maxima has double the width than other secondary maxima and minima. So, just by heart this formula, derivations are not needed. Okay, but just by heart the formula, the angular fringe width and linear fringe width of secondary maxima and central maxima. Clear, children? Now we can see the difference between interference and diffraction. Interference is the result of superposition of two wavefronts from two coherent sources, but diffraction is due to superposition of wavelets from different part of the same wavefront. Second one, all bright fringes have same intensity interference, that is 4I0, and all dark fringes have 0 intensity. But in diffraction, intensity of secondary maxima decreases as we go from the central maxima. Central maxima has maximum intensity, then intensity goes on decreasing, and intensity of minima is approximately 0. Then for bright fringes, path difference is n lambda in interference, where n equal to 0, 1, 2, 3, etc. For diffraction, the condition for path difference for secondary maxima is 2n plus 1 into lambda by 2, where n equal to 1, 2, 3, 4, etc. So, conditions are reversed. Here bright fringe, here this is for secondary maxima, the conditions are reversed. For dark fringe, path difference is 2n plus 1 into lambda by 2, and here for minima, path difference is equal to n lambda. So, here also conditions are reversed. Then fringe width is given by, in the case of interference, fringe width is given by d lambda by d. All the bright and dark fringes have same fringe width, d lambda by d. But in diffraction, central maxima has fringe width 2d lambda by a, and all maxima and minima has fringe width d lambda by a. Central maxima has double width. And angular fringe width for the bright and dark band is lambda by d. In the case of interference, angular fringe width for secondary maxima and minima is lambda by a, and for central maxima it is 2 lambda by a. That is the difference. Okay, so angular fringe width of all dark band and bright band in interference is lambda by d. For central maxima it is 2 lambda by a, and for all secondary maxima and minima it is lambda by a in the case of diffraction. So, these are the main difference between interference and diffraction. Okay.